Hello everyone, I'm Chaitanya presenting on behalf of Team 78. Our topic is Deep Learning Paramedic Assistant for Radiologists. I worked on this project alongside my teammates Abhishek and Sarthak. So, what is the problem we're trying to solve? Uh, we discussed that currently, thanks to the community, efforts have been made to find out millions of labeled dataset of chest x rays. However, there is still a lot of room for improvement when it comes to clinical diagnosis of chest x rays and diseases. Thus, the aim of our project was to be able to build a machine learning model that is robust enough to be able to help doctors by giving an indication of possible diseases after learning from the dataset. Moreover, the model should be adaptive and should readily accept newer training data points as new patients are recognized. The model should also not be susceptible to noise, for example, wearable devices. As in case of any research, before working on the solution, we studied the background of chest X-ray diagnosis in the machine learning domain. CheckSphere dataset is one of the largest publicly available datasets for chest X-rays with more than 224,000 for 65,000 patients with 14 labels. The unique idea about this paper was the labeling strategy that they used apart from the quality control and image preprocessing steps. Another paper we looked at was Chest X-ray 8, which consisted of 108,000 frontal view X-ray images for 32,000 unique patients. The difference being the labels used were 8 instead of 14. Third paper about Chest X-ray 14 uses 112,000 frontal view X-ray images for 30,000 unique patients, and the number of labels here is 14 as well. Segmentation-based deep fusion network is an interesting paper that talks about how do you identify local lung regions from chest X-rays, train them independently, and then fuse them later. As a result, why they use two dense nets, one for independent training and the second one for fusing it later. The dataset used is the NIH benchmark for chest X-ray 14, and it tried to solve two main problems. The first one being unnecessary noise removal, and the second one is to ensure that the image loss is prevented due to lower resolution resizing. The second paper we looked at was supervised learning for pneumonia detection. This was done by Stanford researchers using the NIH dataset. This was a binary classifier which used the ChexNet. And the ChexNet is basically a dense net based network which is 121 layers deep, uses CNNs, and it uses F1 score metric. Now, the first step in case of any data science problem is to clean the data. Real world data is never perfect, and hence pre-processing is a part and parcel. The first step that we did was to look at the data and saw that there were a lot of empty fields and missing values. So we handled them. Second thing we did was to separate RGB values using the Python imaging library. And ultimately what we got was 14 labels, and each of them had 3 values, 1, 0, and -1. However, to facilitate learning via backprop, we recasted the -1 label to 0.5. And the reason behind doing that was to ensure that it does not negatively impact the training. The next step was data processing or filtering. To do that, we used Apache Spark, a popular open source big data processing framework. We used PySpark to clean the data. After cleaning, a custom data loader was created which was responsible for taking the file path name and returning an image in RGB format. One of the critical steps in any data science pipeline is without which ML models would probably not be generic enough would be feature transformation. One advantage about using feature transformation is that it reduces overfitting on the model. Such data augmentation technique lets models see more data than the original available. So as you can see, we have divided into two. There's a train transform and a valid transform. In the train transform, the first step is to use random resize crop. One difference is that it uses randomization, while in valid transform, it uses just the resize. In case of training, it is essential that we don't resize based on some fixed points. The randomized aspect of cropping makes it act like a regularizer, and thus base the classification decision on parts of the object instead of specific distinctive features. The next step is to perform horizontal flip. The intuition behind doing that is that an object should be equally well recognizable as its mirror. Now, specifically in case of chest X-ray images, we recognize that the presence of symmetry about y-axis exists. So we consciously chose not to perform vertical flipping as the lung X-ray images are not circular and not symmetric. However, in case of the model, we incorporated the feature APPA, with which the horizontal flip was taken care of. Last step is to perform normalization, specifically z-score that takes into account the mean and standard deviation. Now, in case of valid transform, the center crop was employed in place of randomized resize crop. Here, the randomization does not really make sense as the model has already been trained and made robust enough. Now, the hope is that the training data has captured all the possible variations of the real world and modeled it correctly. Thus, just cropping validation data is required. Now, training, which is the heart of our project. We trained based on ResNet 18, VGG 11, and Inception v3. All three of them are popular convolutional neural networks, which we were able to train in a sufficient time frame based on the given resource constraints. The notion behind doing the first run and subsequent runs differently is as follows. In the first run, the loss propagation happens on the last layer only and is frozen on all the inner layers of the network. However, on subsequent runs, loss propagation happens in all the layers of the network. The notion behind that is that in the first run, since we are performing transfer learning, we use the weights of the model which have been pre-trained. However, as we go deeper into the training, we want the model to better learn the checked X-ray data, and hence the weight update after loss calculation is propagated through all the layers of the network. We also performed some amount of hyperparameter tuning, that is playing with learning rate, different optimizers, but were met with limited success. So such a training needs to have a robust performance evaluation method. While research paper in our background study, we mentioned ROC-AUC curve, F1 score, precision recall, we explored the possibility of coming up with our own version of evaluation that was used alongside the ROC-AUC scores. The intuition behind coming up with this was because this problem had 14 classes, and there is a non-negligible probability of more than one class being correct. So the existing metrics don't quite capture this. It is ultimately a multi-label, multi-class classification problem. And the caveat here is that some labels are mutually exclusive. For example, no disease versus diseases like pneumonia. That is, they cannot coexist. So this modified accuracy score is calculated as follows. The feed-forward network goes through and gives us the 14 classes. We pass it through a softmax, which gives us the probability values. Now we pass it through an argmax that basically gives us the class with the max probability of occurrence. Now it will either give you equal to 0 or not equal to 0. In case it is equal to 0, there are two possibilities. For label 0, the prediction matches the global truth, and in this case your prediction is correct, and that's why you get a high score. However, if you get that prediction wrong, then you will be graded for the fraction of the rest of the labels that are correctly labeled. On the other hand, when argmax is not equal to 0, and if your prediction is incorrect, we penalize the whole data point and award negative 14 points. So the difference behind using this metric is that it penalizes false positives heavily, as that's the main concern in disease diagnosis. Going further, experiments were conducted. We used VGG networks. The graphs are as follows. Based on the hardware constraints, we came up with pre-trained 11-layer VGG, and the outputs can be seen. Each mini batch is constant, and the training time required is constant after the first one, which takes time to bootstrap the model. The data loader time is minimalized by using appropriate number of worker threads. The next experiment was for ResNet 18. The reason why ResNet 18 has a better accuracy value than the previous one is because it uses identity shortcut connection. Going further, we also experimented by adding two features, sex and APPA, and following graphs indicate that they show similar sort of accuracy in time and loss graphs. Another experiment we performed was with Inception, and as you can see, in case of Inception, the training time is much lesser. However, in case of validation, because Inception requires data to be given in terms of singletons rather than batches, it is much more longer. The losses reduce and the accuracy increases as far as training goes, which is the norm throughout all the three experiments. The best model we found was the one which included ResNet and two fully connected layers. We added additional features And the additional transform added was randomized rotation up to 3 degrees. The loss used was multi-label soft margin. Now this we believe is much more relevant rather than the other losses because it takes into consideration the multi-label. Regularization was dropped out and Adam Optimizer was used. The challenges we faced, the first one was the background domain knowledge. Uh, because this is a biological dataset which consists of 14 different labels, we lacked understanding of the details of observations, the co-occurrences, and correlations. The second one was the resource restrictions. At times, the jobs were killed anonymously. We did not have personal GPUs, and the way we resolved that was by use of Google Colab notebooks, use of pre-trained weights for various models, and suppressing backpropagation on inner layers of the network. The third challenge was high training time, the problem for hyperparameter tuning. The mean training time in Gata collected GPU was 25 minutes per epoch. One total run would take around about 20 hours to run. The way we resolved this was by creating a smaller dataset of about 5,000 randomly selected images. Training took 13 times less, and the hyperparameter tuning was done on this reduced dataset. The contributions, as you can see, it was fairly equal. All of us worked together in harmony, and it was all in all a good project. These are the references, and thank you so much.